Step into the future bright and bold. With TaebiLab where stories unfold. Discover the magic research we unfold. TaebiLab, where science takes hold.
Welcome back to another deep dive with us. Today we're really going deep into some fascinating research
Oh, yeah.
on cerebral aneurysms.
Yeah.
And you might remember that we are going through a series of publications from TaebiLab. This is actually our fourth episode in this series. And I should mention at top that we're using a bit of AI to help us in this episode.
Right.
Kind of synthesize the information.
Yeah.
So,
It's really amazing how AI can help make some of this complex research.
it is more digestible.
It really is, and approachable.
Yeah.
Okay, so let's get into the paper itself.
Okay.
The paper is titled Variations of Middle Cerebral Artery Hemodynamics Due to Aneurysm Clipping Surgery.
Right.
And it was published earlier this year.
In the ASME Journal of Medical Diagnostics.
Yeah.
Earlier this year, 2024.
Yeah, and you'll see the names of Davidson, Scardino, Pishala Thibotuwawa Gamage, and Amirta Taebi listed as the authors.
Yes, that's
on the paper.
So now, for those who aren't familiar, cerebral aneurysms. These are bulges that can form in the walls of arteries in the brain.
Yeah.
And they're serious.
Yeah, they're serious.
Because if they rupture, they can cause a hemorrhagic stroke,
Exactly.
which can be life-threatening.
Yes, and surgical clipping is one of the main ways we treat these aneurysms, and it involves placing a small clip on the neck of the aneurysm to stop blood flow into it.
Okay.
But as you can imagine, altering blood flow in such a delicate area can have ripple effects.
Wow.
And that's what we were really trying to understand better in this study.
So the big question is, how does clipping actually change blood flow in the brain?
Right.
And what are the implications for patients? It sounds like you use some pretty high-tech tools to
investigate this. We used computational fluid dynamics, or CFD for short.
Okay.
It's a way to simulate how fluids, in this case blood, flows through complex structures. And we used 3D images of cerebral arteries from a database called Aneurysm and some pretty sophisticated software to build incredibly detailed models of the arteries.
So you're essentially creating a virtual version of the patient's brain and blood vessels.
Exactly.
And then you can simulate
Yes.
how blood flows through them before and after clipping.
That's a great way to put it, yeah.
It's like having a window into the brain's plumbing.
Yeah. We actually focused on two specific cases from the database. One patient with a small aneurysm and another with a larger one. This allowed us to compare how clipping might affect blood flow differently depending on the aneurysm size.
Clever.
Yeah.
Now, I'm sure there were some challenges along the way.
Oh, for sure.
What were some of the hurdles that you had to overcome in creating these simulations?
One of the biggest limitations was the lack of patient-specific blood flow data in the Aneurysm database. We knew the shape of the arteries, but we didn't have detailed information about how fast the blood was flowing in each patient.
So you had the map of the roads,
Exactly.
but not the traffic patterns.
Right.
That sounds tricky.
We had to make some assumptions and use a generalized blood flow pattern for our simulations. It's like assuming everyone on a highway is driving at the speed limit, even though we know that's not always the case.
Right. There are always variations in real life.
Right.
So how did you account for this limitation in your study?
We were very transparent about this limitation in our paper.
Yeah.
It's something that we definitely need to address in future research. Ideally, we'd have access to patient-specific blood flow data, so we could create even more accurate and personalized simulations.
So future studies could fine-tune the simulations by factoring in individual variations in blood flow.
Exactly.
Okay, that makes sense. What were some other areas where you saw room for improvement?
Well, another area is the validation of our findings. Computational models are powerful, but we always need to check how well they reflect reality. We need to compare our simulation results with actual measurements of blood flow in patients, perhaps using techniques like Doppler ultrasound.
So it's like checking your map against what you actually see.
Exactly.
When you're driving.
Exactly.
That ground truthing is
It's essential in any scientific field.
essential.
Yeah.
Absolutely. And then, of
course, there's the question of long-term effects.
effects. This study focused on the immediate changes in blood flow after clipping, but what happens in the months and years that follow? That's something we still need to explore further.
So it's not just about the initial impact,
Exactly.
but the long-term implications as well.
Right.
It sounds like there's a lot of exciting avenues
Oh, yeah.
for future research in this area.
There really is.
Hmm.
This was just a pilot study with a limited sample size, but it's laid the groundwork for more in-depth investigations.
Well, I'm eager to hear about the specific findings from this pilot study.
Okay.
What did your simulations actually reveal about the effects of clipping on blood flow?
Sure.
Let's delve into that after a quick break.
For every heart, science light where shadows start, monitoring day and night, healthy beats in future sight, heartbeat, harmony.
Okay. All right, so let's get into some of the specifics. One of the things we were interested in was how clipping affects the speed and direction of blood flow. We looked at what's called axial velocity distribution, which essentially tells us how fast the blood is moving along the length of the artery.
So imagine blood flowing through a pipe. Axial velocity tells us how fast the water is moving down the center of that pipe.
Exactly.
What did you find? Did clipping change the speed limit in those arteries?
We did see some changes, particularly in the patient with the larger aneurysm. Clipping seemed to alter the speed of blood flow more significantly in that case.
Makes sense that the size of the aneurysm would play a role. What about the direction of blood flow? Did clipping affect that as well?
It did. We observed some interesting changes in what we call secondary flow patterns. Imagine those swirling eddies and currents you mentioned earlier.
Right.
Clipping seemed to disrupt those swirling patterns, especially near the aneurysm site.
So it's not just about the overall speed of blood flow, but also these more intricate patterns
Right.
within the flow. And why are these swirling patterns so important?
They can influence the forces acting on the artery walls. High forces, especially concentrated in certain areas, can weaken the walls and increase the risk of the aneurysm rupturing.
That makes sense.
Yeah.
So understanding these secondary flow patterns could be crucial for predicting the long-term stability of the aneurysm after clipping.
Exactly. And that's one of the real strengths of CFD. It allows us to visualize and analyze these complex flow patterns in a way that's simply not possible with traditional imaging techniques.
It's like having a magnifying glass
Yes.
for the brain's blood flow.
Exactly.
Now, you also mentioned something called wall shear stress
Yes.
in your paper. Can you explain what that is and how it relates to aneurysms?
Sure. Wall shear stress, or WSS, is basically the frictional force exerted by the flowing blood on the artery walls. Think of it like the force you feel on your hand when you hold it out the window of a moving car. The faster the car goes, the stronger the force.
Okay, so it's the drag force of the blood against the artery walls. And I imagine this force can put stress on those walls, especially in an area where there's already a bulge like an aneurysm.
Exactly. High WSS has been linked to an increased risk of aneurysm rupture. That's why it's such an important factor to consider.
So what did your simulations reveal about how clipping affects wall shear stress? Was there any good news on that front?
There was. We found that clipping led to a decrease in WSS within the aneurysm itself. That's encouraging because it suggests that clipping might actually reduce the stress on the aneurysm walls, making it less likely to rupture.
Okay, so in that sense, clipping seems to have a positive effect.
Mm.
But I recall you mentioned an unexpected finding related to WSS. Could you elaborate on that?
Sure. While WSS decreased within the aneurysm, we noticed a slight increase in WSS in the branches upstream of the aneurysm. After clipping, this wasn't something we were specifically looking for, but it's definitely something that warrants further investigation.
So while clipping might relieve stress in one area, it might potentially increase stress in nearby vessels. That sounds like an important caveat.
It is. We need to understand whether this increase in WSS upstream of the aneurysm has any clinical significance. It's possible that it's a negligible effect, but it's something we need to study further.
Right. It highlights the complexity of the brain's circulatory system and how even a seemingly localized intervention like clipping can have wider repercussions.
Absolutely. It's a reminder that we need to be very thoughtful and meticulous when we intervene in such a delicate and intricate system.
You mentioned earlier that this was a pilot study with limitations.
Yeah.
Are there any other areas where you see the need for more research?
Definitely. We need to explore the long-term effects of clipping on WSS in those upstream branches. We also need to investigate how different gluing techniques and clip placements might influence blood flow dynamics.
So there are nuances to the surgical procedure itself that could affect blood flow.
Exactly.
That makes sense. Are there any other factors you'd like to investigate in future studies?
One area that I'm particularly interested in is the role of patient-specific factors like age, blood pressure, and even lifestyle choices.
So how individual variations beyond just the anatomy of the aneurysm itself might affect the outcome of clipping. It sounds like you're moving towards a truly personalized approach to understanding and treating cerebral aneurysms.
That's the goal. I believe that by combining advanced computational modeling with a deep understanding of individual patient characteristics, we can make significant strides in improving the way we treat this challenging condition.
It's a powerful vision, and I'm excited to see what you and your team uncover in your future research. But before we get ahead of ourselves, let's bring it back to the present and recap some of the key takeaways from this particular study. What are the most important things you want our listeners to remember about this research?
Okay, so let's recap what we've learned here.
Yeah.
You use sophisticated computer simulations to study how surgical clipping affects blood flow in the brain for patients with cerebral aneurysms.
Right.
And you found that clipping does alter blood flow.
Yep.
And those changes can vary depending on the size of the aneurysm.
That's right. And one of the most important findings was that clipping can actually reduce stress on the aneurysm walls,
Right.
potentially making it less likely to rupture in the long run.
Exactly. And it's important to remember this was a preliminary study,
Right.
kind of a stepping stone to more in-depth research.
Yeah.
We need more data, especially patient-specific blood flow information,
Yeah.
to refine our models and gain a more complete understanding of the long-term implications of clipping.
And you also mentioned the potential for incorporating factors like age, blood pressure, and lifestyle choices into future simulations.
Definitely.
It's fascinating to think about how these individual variations might influence the outcome of clipping.
Absolutely. Every patient is unique, and I believe that incorporating these personal factors into our models will be key to developing truly personalized treatment strategies for cerebral aneurysms.
It sounds like you're paving the way for a future where treatment decisions are tailored to each individual rather than relying on a one-size-fits-all approach.
That's the vision. I believe that computational modeling combined with a deep understanding of individual patient characteristics has the potential to revolutionize how we treat cerebral aneurysms.
It's a powerful vision, and one that gives hope to countless individuals and families affected by this challenging condition. Well, we've covered a lot of ground in this deep dive. We've explored the intricacies of cerebral aneurysms, the challenges of surgical clipping, and the power of computational modeling to shed light on this complex medical puzzle.
And we've only just scratched the surface. There's still so much to learn, but I'm incredibly excited about the future of this research and the potential it holds to improve the lives of patients.
I share your enthusiasm. It's inspiring to see how dedicated researchers like yourself are pushing the boundaries of what's possible in medicine. And to our listeners, thank you for joining us on this deep dive. We hope you found it informative and thought-provoking. If you want to delve deeper into this research, we'll provide links to the original paper and other resources in the show notes. Until next time, keep those brains buzzing.